Welcome to second part on principal stress and strain. And last part we consider only the analytical method for stress analysis. Here we are approaching graphical analysis. So most of the questions in competitive examination are coming from Mohr circles. So we can start before going to the Mohr circle. Just a glimpse I'm giving about analytical analysis. So for analytical purpose, the normal stress acting on an arbitrary plane which is at an angle theta with the vertical is given by this formula, and corresponding shear stress is given by this corresponding formula. So this is regarding the analytical section. Now we are going to a graphical method, Mohr circle. Before going to the graphical construction, I just want to discuss about the theoretical part. Why is a circle that shear stress and normal stress can be represented? So again come to the analytical part. Suppose this equation sigma n, that is a normal stress on an arbitrary plane at an angle theta with the vertical, and this is a shear stress acting. Suppose we can rearrange this value into sigma n minus sigma x plus sigma x by 2, the whole square value. The right hand side goes to sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta, the whole square value. Similarly, if we square this equation, the term we will get, that square will be equal to minus sigma x minus sigma y by 2 sin 2 theta tau xy cos 2 theta, the whole square value. Suppose we take the square value, cos square theta, sin square theta, that will goes to cancel. The rest of the term we will get, that will look like this term. So our duty is to add this is equation B and this is equation A. Add these two, we will get the expression like this. So we get an equation like this, which is similar to an equation x square plus y square is equal to r square with a, this is circle equation with the center. Now there is some variation, that is in the place of x there is a term, a constant x plus y divided by 2. So I can consider like this: x minus a the whole square plus y square is equal to r square, where r is going to be the radius and a is going to the corresponding coordinate of center of that particular circle. If you plot the circle, that will be look like this. It will be symmetric about the x-axis. So from that perspective, we can say the Mohr circle can be constructed with the sigma, that is a normal stress at an arbitrary plane along the x-axis, and a shear stress along the vertical line. So if we construct such a poster circle, so the circle with the center sigma x plus sigma y by 2 comma 0 and a radius value equal to this term, that is square root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square value. So that will be the radius. Therefore radius we can say square root of sigma x minus sigma y by 2 the whole square plus tau xy whole square. So these 5 properties of Mohr circle you should remember in mind. Questions will be based on these basic ideas. Center of Mohr circle always lies on x-axis, that is it will be symmetric about the sigma axis. So circle will be like this. Then the radius of circle gives the maximum shear stress. So we obtain the expression for shear stress. Shear stress is nothing but the radius we got. R is equal to this term. So in the previous section, analytical section, we discussed about the maximum shear stress formula. It is very similar to this quantity. So we can say the radius of circle gives the maximum shear stress. Then coordinate of center represent normal stress on the plane of maximum shear stress. So that will detail discuss on the construction of Mohr circle. Then at any hydrostatic loading, Mohr circle will be a point. So hydrostatic loading is a case when the object is subjected to equal magnitude stress in all directions. For example, this cube is subjected to a hydrostatic load in all phases with a value of sigma. So in such a condition, there will not be any shear stress development. So we can say shear stress is 0. The radius of the circle is always equal to the maximum shear stress. So shear stress value going to be 0. Definitely the circle will be represented as a point on the axis. Then for pure shear loading, center of Mohr circle will coincide with the origin. Definitely the center or the coordinate of center is given by sigma x minus sigma y by 2 comma 0. In the pure shear loading condition, sigma x become equal to sigma y value. Definitely that coordinate will going to be 0. So origin, sorry, sigma x plus sigma y. Okay, so sigma x, sigma will both will be 0. So 0 will be the corresponding coordinate. So now we can discuss the construction of Mohr circle. The case 1, which is a simplest form of loading, that is a uniaxial loading on a isotropic material. In order to construct, we have to find out a graph, a coordinate system. Here the sigma x value I am just taken as a sigma value, and the sigma y, that is stress acting on the y direction, is taken as 0 because there is no loading exist, and shear stress acting is also 0. So from the basic idea of Mohr circle, the center of Mohr circle always lies on the x-axis. Okay, then radius of circle gives the maximum shear stress. So maximum shear stress formula, tau max is equal to root of sigma x minus sigma y by 2 whole square plus tau xy whole square value. So here tau xy is 0, that gone, sigma y is 0. So what is the rest of the value? We get that root of sigma x by 2 the whole square value. So we will get the sigma by 2 itself. So we identify that the radius of the circle for this particular case will be sigma by 2. Now coming to the coordinate of center represent the normal stress of the plane of maximum shear. Then the x coordinate, the coordinates for the circle of circle center is given by this coordinate, sigma x plus sigma y by 2 0 value. So center we can find out sigma plus 0 divided by 2 0, nothing but sigma 2 0 value. So now we identified that the radius of the circle will be sigma 2, and center coordinate, that will be sigma by 2 0 value. So we can find out this value. So along the x-axis, horizontal axis, we can mark a sigma by 2 distance. That will be the corresponding coordinate, 0 coordinate. Now take the sigma by 2 in a compass and construct a circle with the center sigma by 2 0. So this is sigma by 2 now. So this is a Mohr circle for this particular loading. Now if you want to find out the stress acting along an arbitrary plane, which is make an angle theta with the vertical, we can construct the Mohr circle itself. So sigma x axis, that sigma axis corresponding represent the stress point where there is no shear stress. We know the principal plane, that is sigma x is acting about perpendicular to this particular plane. Definitely if an angle theta is if you want to find out a stress along a plane which is at a theta angle from the principal plane, definitely we have to construct a 2 theta angle subtension, then we can find out another point. So this plane corresponding to the theta on the object itself. Now if we connect with the origin and this point O, then the corresponding vertical drop, this will be the corresponding shear stress acting on the body, and this much portion is corresponding to the normal stress acting on that particular plane. That's a construction. So in order to find out the normal stress acting on this particular plane, you have to construct a 2 theta angle, then completed this and find out the point O, then connect it with the origin. So I just denote this O dash value. So corresponding horizontal coordinate of this point O dash gives the normal stress acting on the plane, and the vertical coordinate corresponding gives the shear stress acting on that object, or especially on that particular plane. Now this is another case, the biaxial loading without any shear stress. Starting from the basic idea, the radius will be the corresponding maximum shear stress, so that will be square root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square. Since tau xy is not present, that's going to be 0. So this value sigma x minus sigma y by 2 will be the corresponding radius. And the center of circle will be always sigma x plus sigma y by 2 comma 0. So with this information we can consider a circle on this graph sigma and a tau value. Another way we can construct this as by plotting the respective sigma x and sigma y. Suppose sigma x is greater than sigma y value. I just mark first sigma x from 0 to this point. So this much distance is nothing but sigma x. Now I can construct another point sigma y if this value is sigma y. So tau value is shear stress is 0. Okay, then we just can find out this much distance and make or find out the center point. And keeping this at the center, I just going to draw a circle. Then that circle will be corresponding with a radius value sigma x minus sigma y divided by 2 and the center sigma x plus sigma y by 2 comma 0. So this is the construction. Same as discussed earlier, if you want to find out the normal stress acting on a particular plane which is at angle theta with the sigma x longitudinal direction, then construct a 2 theta angle and make this joint and find out a point O dash and connect it with the origin. Then the corresponding vertical drop corresponding gives the shear stress acting on that particular plane sigma xy dash, and the horizontal component will give the normal stress acting on that particular plane sigma n dash value. So in the same case there is another chance of question will come, that is sigma x is tensile and sigma y is here compressive in nature. So in such a case, how we will construct the Mohr circle? So again we will go for a coordinate system. We will develop a coordinate system. So sigma x is positive, so we will take the positive x-axis as a positive, same convention, final convention, but sigma y is negative, so you have to go for sigma y value. In such condition, if you want to construct a circle, we will again find out the length of this strip and find out the center, then make it center and construct a circle. So that's a circle. If you want to find out any stress at any arbitrary plane, you have to make a 2 theta angle from the x-axis from the origin, then connect with the corresponding origin. Not you have to make the theta with the center. Then the vertical component corresponding gives the shear stress, and horizontal component gives the corresponding normal stress at that particular plane. So this is another case, that is biaxial stress. Also there is a sigma tau xy is also applied, shear stress is also applied. So in such condition, again we will start with the basic idea. The center coordinate that will be always given by sigma x plus sigma y by 2 comma 0 value, and the radius of the circle will be always corresponding maximum shear stress. It is given by sigma x minus sigma y by 2 the whole square plus tau xy the whole square value. While coming to the geometrical construction, first of then same method we have to adopt. First sigma x should be marked. Let this be the sigma x distance, and sigma y, since it's a tensile same positive x-axis direction, we will mark the sigma y also. Then coming to marking of shear stress. So this is a positive shear stress loading. We mentioned in the analytical method that this is a case of positive shear loading and this is a case of negative shear loading. Okay, so it's a positive shear loading. So basic procedure is you have to split this shear into horizontal and vertical component first. That order you have to remember. Suppose this first one you have to create in a horizontal manner, then split in plus the vertical thing. So So this is a horizontal one, and plus this is a vertical component now. Now horizontal that's a clockwise, that is taken as positive, and this one is negative, your tensor negative. If it is clockwise positive, there you have to put in the above x-axis. If it is negative clock moment is making, and you have to drop into the downward direction, that is in the negative y-axis direction. Here the clockwise, that is positive, so you have to drop in the upper direction tau xy value. You have to scale down and mark it, and again from sigma y you have to mark the tau xy. Then just connect the tip of this two value, then you will get a intersection with the x-axis. That should be the center for corresponding Mohr circle. Then you have to make a circle with the radius this much. Okay, so construction wise we got the circle now. So check the radius of the circle. Look at this figure. This much distance is nothing but sigma x minus sigma y value. Half of this value goes to this side, and tau xy going to be this side. So when considering a right angle triangle, this radius is nothing but the hypotenuse of this right angle triangle. So definitely radius become this quantity. Now the construction is over. If we want out the stress at any arbitrary plane which is at angle theta with the vertical, definitely with the center you have to make a 2 theta angle section, then corresponding point O dash connected with the origin. So the vertical portion gives the corresponding shear stress on that arbitrary plane, and the horizontal distance gives the corresponding normal stress on that plane. So in hydrostatic loading, from all directions, the object will be squeezed or supplied with the same magnitude stress. Definitely the radius of circle become corresponding root of sigma x minus sigma y by 2 the whole square plus tau x y the whole square value. That value is going to be 0, and the center of circle, that is going to be sigma x plus sigma y by 2 comma 0. Definitely sigma by comma 0 will be there. So if we consider a graph for x and y coordinate, then the circle will be denoted with the sigma with the center sigma comma 0 and radius 0. So it will be a dot point. So another case we can discuss, that is a pure shear condition. Only shear stress is applied. So in such a condition, the radius value we will obtain that sigma x minus sigma y by 2 the whole square plus tau x y the whole square. This is going to be 0 value. Root of we will get the tau with radius tau value, and center value we will get sigma x plus sigma y by 2. Since both the stress are 0, this value going to be 0 0 coordinate will be there. So by constructing a circle, the circle will be symmetric with the origin. Center will coincide with the origin with the radius tau value. So this will be the corresponding shear Mohr circle for